Units for electric field. Forgot to mention units. What is it? It's force divided by charge. The units for force, newtons. The units for charge, coulombs. So a newton per coulomb is what we're using right now for electric field. As we get into other next chapter, we'll see that there are other units that are acceptable also for electric field, but right now newtons per coulomb. And what we want to do so we've talked about the fact that we can link these together with superposition. If we have multiple point charges, we just add up the electric field due to each point charge. It's vector addition. This is a vector quantity. And we've talked about the fact that these electric field lines, we want them to, they have certain rules that we follow when we draw them, right? They originate on positive charges. They terminate on negative charges. And the number of field lines is proportional to the charge. So you can see that these two charges both have the same number of lines that originate or terminate on them. So those two charges would be equal in magnitude. One of them, the lines go into, that's the negative charge. One they come out from, that's the positive charge. Over here, one charge is twice as much as the other one. So if you count the lines carefully, you'll see twice as many field lines drawn there as on this one. These two are equal in magnitude, so the same number of field lines. So the number of field lines proportional to the charge. The direction depends on whether they originate or terminate on, which charge they're originating and terminating on, right? Positive charge, they come out from the positive charge, they go into the negative charge. And the fact that we can take a very quick look at this now, and we can tell that the electric field, this is the third point, the electric field is weakest where those lines have the lowest density. It's strongest where the lines are most dense. So you can see as you get closer to a charge, the electric field gets stronger. As you move away, those lines become further and further apart. So as you get closer to a charge, the field increases. In here, you'd see it's fairly strong. Out here on this side, it's fairly weak. So you can tell from the drawings then, if you draw them carefully, that the field is strongest in certain places and weaker in other places. So it's a nice tool. These electric field lines are a nice tool for us. Shielding and Gauss's law. Let's talk about Gauss's law first. And flux. So flux, let me introduce the concept of flux. The idea behind flux, this is, right now we're going to be talking about electric flux, where electric field lines penetrating a surface area. In a few weeks, we'll be talking about magnetic flux, magnetic field lines that penetrate a surface area. And to maybe give you a simple analogy of flux, let's pretend we were going to go fishing at a river. There's our river. And for simplicity, I'm going to make my river special. The flow of water is uniform across the entire river. Of course, real rivers aren't that way, right? They are fastest in the middle and slowest at the banks. But let's just pretend the water moves uniformly across our river, and we're trying to catch a fish with our fishing net. So we stick our fishing net into the river. Maybe our fishing net is oriented something like this. How would we orient our fishing net so that we might catch a fish? Would we put our fishing net in like this? No, right? Fish is never going to go through that net. Nothing's penetrating the net, right? So in terms of flux, we would say the flux is zero. There's no water penetrating the area defined by my net. So if I tilt it a little bit like this, I've got, what, at least a little bit of a chance now I'll catch a fish. If I keep increasing the angle, I eventually get to a maximum possibility of catching a fish, right? If I continue to roll it over, my probability goes down. I've got less and less water penetrating through my fishing net. So that's what we call flux. In this case, it's water penetrating through the net, but right, so in this case, I would say that corresponds to zero flux. There's no water that penetrates through the surface defined by the fishing net. In this case, we've got a little bit, right? This would have a small flux. And in this case, we have the most. This is our maximum flux. So it's the amount of something that penetrates some surface area. In this case, water penetrating the surface area defined by the net. And in our electrical case, it's electric field lines. We have this symbol for flux, electric flux. It's the electric field lines multiplied by the area. But what else? Let's take a look at our fishing net, for example. What's going to change the flux? What's going to increase our probability? What are some of the things we can do to increase our probability of catching a fish? Change the angle, right? So I need some angular dependence here. What else would I do? Get a bigger net, right? That's why I have the area here. Right? Get a bigger net. Increases my chance of catching a fish. What else can I do? If I'm PG&E and I have a turbine up at the top of the river, I could increase the flow of water, right? You or I can't do that, but if you happen to have the dam, you control the dam up at the top of the river, maybe you can increase the flow of water. That's what this is, E, right? So what can we do to increase the electric flux, the number of electric field lines that penetrate a surface area? We could increase the electric field. We could increase the area. Or we could try to maximize the amount of field lines that penetrate the area by making the surface perpendicular to the electric field lines. How do we define a surface? We like to use a vector to define something, right? Well, if you put a vector inside of a surface, no matter where, if I'm trying to define the surface of the screen, I put a vector in the screen, I could put it any orientation. It doesn't really help me define the plane of the screen. But if I put it perpendicular to the screen, that defines the plane of the screen very clearly, doesn't it? So that's what we use when we give a surface area a vector to define the surface area. We use the normal to the surface. So the normal to this surface, I'm going to draw it in red here. The normal to the surface points like that. And that's why there's a cosine theta here and not a sine theta. I know you were wondering about that, weren't you? It goes to 0, right? This is the case where we get 0. And you're thinking to yourself, wait a minute, the plane of my fishing net is parallel to my water vector lines, right? Why does the cosine theta come in? That should give me a 1. Well, it's because we use the normal to the surface. So the normal to the surface points up. My field lines point to the right. That's a 90 degrees. Cosine 90 degrees gives me 1. It gives me 0, right? And in this case over here, the normal to my surface points this way. And my field lines also point that way. So I get a cosine 0 degrees. I get my maximum flux. I just multiply the electric field times the area. If the electric field is constant over the area, I can do that. If it's not, then you have to integrate. But since we don't integrate in this class, the electric field will be constant over the area. Okay, so I'll just write that here. Okay. So what we're going to do is a little worksheet that walks us through coming to grips with Gauss's law. And let's start out with the charge detective side.